So once we have met all of our assumptions for regression inferences, we can now look at and decide whether X is actually useful as a linear predictor of Y. That is, whether this regression equation has utility by performing a hypothesis test. So again, we're looking at how useful is X as a predictor for Y. And before we do that, I want to go back to slope for a second. We talked a little bit about this in chapter 14. If we had some data that really had that appeared to be unrelated, you can kind of assume that we would just be able to draw a perfectly horizontal line. And we know that perfectly horizontal lines have a slope of 0. So what we're trying to determine is if our sample data has enough evidence for us. So here we have some sample data that appears to be a little more linearly correlated than a little bit more of a linear regression than the one above, and to see if our sample data is going to provide us enough evidence that our slope is anything but 0. Not 0. If our slope is not 0, then we could say that there is some utility to our regression line. And we can actually use that regression equation to make some inferences about the population. So to do this, let's take a look. Let's go back to that data we were working on in the other lessons. And this had to do with the study time over 2 weeks. X represents study time and Y is the response variable, which is your grade on the test. And if you recall in the chapter 14 videos, we found our regression equation to be y hat equals 94.867 minus 0.846x, which tells us, of course, you can identify the y-intercept from that sample is 94.867, and the slope from our sample regression line is negative 0.846. So here's the question we want to ask when we're looking at this. And this is the question you're gonna get when you're working out these problems. At the 5% significance level. So that right there should tell you that you are going back to a hypothesis test. Do the data provide sufficient evidence to conclude that, in this case, study hours, the number of hours studied is a useful linear predictor of the grade you will get on a test. So the key word here is usefulness. And that's what we're looking at. And that tells us that we are going to look at the slope to determine usefulness. And you can kind of take a look at your formula sheet, of course, when you get down to chapter 15. Here it is, test statistic for H sub O. Your null hypothesis is going to start with the assumption it's not useful. Remember, the data then has to come out and tell us that it is useful. So we're going to start with this null hypothesis for all of these particular problems is not useful. So the other thing to keep in mind is small b sub O is your sample. we are going to look at, when we're doing our hypothesis test, we refer to the population variable. And that's capital B sub 1. Small b sub o and small b sub 1 represent the sample. So small b 1 is the slope of the sample. We are going to look at is the slope equal to 0. Okay, using the population slope, of course. Same way when we look at means, we use mu in our setting up our null and our alternative hypothesis. Having it equal to 0 means not useful. All right, X is not a useful predictor of Y. Done. Our alternative, of course, is it useful? So that means B sub 1, and it doesn't matter if it's negative or positive. You just want to say, hey, B sub 1 is not equal to 0. That means useful. Okay, there is no other null or alternative hypothesis you're going to use in this particular section when dealing with usefulness of your regression equation. Now, go back to your formula, and let's get our test statistic. So we're going to go back to our t-table. We're going to go back to t-test statistics. Here's your formula. Notice it's B sub 1, because of course, when we're calculating the test statistic, we have to use the slope we know, which is the slope for our sample. So let's write this out. Your test stat. So step 1, of course, is setting up your hypothesis. Step 2 is getting all our information. But before we can get all our information, we need to know our test statistic, which is lowercase b sub 1, the slope of the sample. And then it's, take a look again. See, SE over the square root of SXS. So we'll just write that down for a second. And the square root of SXX. Okay, so I'm going to go back. And we need to figure everything out. All right, we know B sub 1. That is our sample slope. You will get that from your regression equation. Make sure you use the correct sign with it. It's negative 0.846. We also need an S sub B. I talked about this in the last video with residual plots. That is the standard error of the estimate. The formula is here. It's kind of like stating this is the standard deviation of all your residuals. Residuals represent those E values that is the difference between our raw value of Y and what we would get if we used the regression equation. So the formula for that is the square root of SSE over n minus 2. And because this is a problem we've already worked on, you are not going to have to recalculate these for every problem, of course. We can just look back at a past problem to get our SSE. Now, notice when we did our last, when we did coefficient of determination and correlation coefficients, we found the sum of the squares of the regression, and we found the total sum of squares. But one of the key things I had pointed out at that time was this idea of a regression identity. Your total sum of the squares is the sum of the squares of the regression plus the sum of the squares of the error. We went over that in a graph in the last section. So we can use that regression identity to find SSE, because the 188 is going to equal 112.9 plus SSE. So take a minute real quick and calculate SSE. And it looks like it should be, right, I forgot to put a number in. $75.1. So we have square root of 75.1 over n minus 2. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 2 is 6. Divided by 6. Take the square root. it's 12.52. Take the square root of that. It appears to be about, let's round it to 3.54. So for SE, we get 3.54. The other value we need to calculate this t-test statistic is XX, and that you would have gotten in a previous part of this problem. I have it up there. It is 157.86. And you can go back to, I think, the video I did on the regression equation, part 1 and part 2. Part 1 will have that on there. So now that we have our values, we can plug them into our test statistic. Oops, I don't want to go quite that small. So our slope, of course, was negative 0.846. SB is 3.54 over the square root of 157.86. Go ahead and get that. So I got negative 3.003, and of course, if I made a mistake, you can send me an email. I'll fix it. Let's do a quick critical value approach. We haven't used the t-table in a while, but go ahead. You do your critical value approach. Remember, we're back to t curve. Go back to your alternative hypothesis. You see that this is not equal to, which means it is two-tailed. Our degrees of freedom are n minus 2. So the degrees of freedom, which we didn't put here, but degrees of freedom should be 1, 2, 3, 4, 5, 6. So yeah, 8 minus 2. So you have 6 degrees of freedom at a significance level of 0.05, which is what I gave you in the original problem. So go ahead, go to your t-table. Now keep in mind, because this is two-tailed, that 0.05 has to be split between those two tails. So we're looking at 0.025. So we want t of 0.025 at 6 degrees of freedom. Please take a look at your t-table to make sure you know where that is. I'm getting 2.447. You go ahead and put that in the positive and the negative. And then we can see that our test statistic of -3 falls just in the rejection region. So we would reject the idea that the slope is 0, and we would conclude at, this is your step 5, the 5% significance level. The data do provide sufficient evidence that the hours a student studies is a useful predictor of test score. So I know that's sloppy, but at the 5% significance level, the data do provide sufficient evidence that the number of hours studied is a useful predictor of the test score. In the next and last video, we're going to look at another way to see the relationship between X and Y.